dynamic equilibrium section. And so you may notice next to each question, there's maybe a little C and K written out. And so C and K stands for content and knowledge. And that makes up about 30% of the grade for Chemistry 12. Sometimes you'll see an FS that stands for foundation skills, which works out to about 15% or so of our Chem 12 grade. And then you have these 3C markings next to the question. That means, of course, creative, collaborative, and critical thinking. And that's about 50% of Chem 12. All right. Now, with that in mind, so we're going to go over question 1 to begin. That's a content and knowledge question. All right. So this is our unit review solutions. Okay. Pen is on his last days. All right. So let's start with question 1. Asks, okay, what does it mean for a reaction to exist in dynamic equilibrium? All right, so there are a lot of acceptable answers here, but this is open enough that this would probably be something like a 3 or 4 mark question, and I would expect roughly 3 or 4 different points for what this means. Okay. I'm going to outline my first thoughts here. So, okay, so point form is acceptable for a question like this. So, dynamic, let's start with equilibrium. Equilibrium means there is no change in concentration. Dynamic means a constant exchange of reactants and products. So reactants turn to products, and products are also turning to reactants. Okay. Now, how can we balance these two ideas? Equilibrium means there's no change in concentration, but dynamic means that reactants are always turning into products, and products are always turning into reactants. So, dynamic equilibrium refers to a reaction in which the number of reactants turning to products is equal to the number of products that are turning into reactants. So that means if I've got my reactants and my products, the rate is equal to some value x, and that rate of turning reactants into products, which is some number, doesn't matter what it is, it's constant, and it's the same as the rate of turning products into reactants. These happen at the same rate. And the result is is no change in concentration despite consistent exchange of products and reactants. Okay. There are, I guess, a couple other ideas. The ratio of products and reactants is fixed and is abbreviated, called the equilibrium constant, KEQ. Equilibrium means that the entropy and enthalpy fundamental forces oppose each other. Okay. I'd say that's fine. I wouldn't want to go into anything else. That would be, I'd say, a 5-star answer. You would for sure get all the marks in a question like this. However, the instruction is a little vague, and if this was a test, I would try to be a little bit more specific as to what I was looking for. But the big hint would be how many marks it would be for. So the number of marks would reflect, I think, how many really essential points to know about equilibrium I would want you to list. And so I could think of 5 off the top of my head to adequately define dynamic equilibrium. And for you guys, I might expect you might be able to give me 4. And if you could do all 5, well, that would be even better. All right, let's move on. Question 2. Question 2 says, for the following reaction, select all that apply. All right, so I'm going to record my answers for question 2 on this page. Okay, so we've got this reaction. It looks like it is exothermic. Looks like the enthalpy and the energy in these bonds is being lost to the system, to the environment, to the universe. We're losing energy, and that means this is exothermic. Okay, so we know it's exothermic. All right, so let's take a look at some enthalpy arguments. All right, maximum enthalpy favors the reactants. Well, if I look at where the reactants are, it looks like their enthalpy is higher than the enthalpy of our products. Yeah, so for sure, the reactants demonstrate they have a higher level of enthalpy, which means the maximum enthalpy can't favor the products. The minimum enthalpy doesn't favor the reactants. That's the opposite of saying the maximum enthalpy favors the reactants, so that can't be right. But the minimum enthalpy, the smallest amount of enthalpy, looks like it is with the products. This is the enthalpy of our products here. This is enthalpy of our reactants. And we can see the reactants have a maximum enthalpy, products have a minimum enthalpy. And so we talked earlier here about this idea that when a reaction is exothermic, there's a loss in enthalpy from the bonds, and I guess the temperature as well of these reactions. And so that means that we say the change in enthalpy is negative. And that's because change in enthalpy is delta means final minus initial. Or in chemistry, it means products minus reactants. So it doesn't really matter what our values are here. If I know that this number HP is smaller than my enthalpy of my reactants, and the change in enthalpy is I'm going to be taking away a larger number from a smaller number. So my change in enthalpy is going to be negative. All right, so that means my delta H is negative. And we talked about how this reaction is exothermic as a result. Yep. Okay, cool. Now with minimum entropy for the favors of products. All right, so let's look at entropy. So entropy is pretty easy in this case. We're looking for the term with the most number of species in the most random phase. So the most random phase is a gas. And it looks like this side doesn't even have any gases. So because this one has 3 gases, gas molecules, we're going to say that the reactants have a high entropy. High degree of randomness. Gases are hard to contain. They're flying everywhere. A solid is just going to sit there and you go back later and it's still there. And that's especially frustratingly true with rust. If your car begins to display rust and you walk away from it and you go back, that rust is still going to be there. This is rust, in case you were wondering. This is iron, oxygen. This is the oxidation of iron to turn into rust. Okay. Okay, so that means the minimum entropy favors the products. And that's not right. This is a low entropy system. Our minimum entropy favors the... minimum entropy. That is right. Because we have a high entropy system here. So our maximum entropy favors the reactants, which means this one must be wrong. Okay, so then the question is, okay, what kind of reaction do you have? So it looks like entropy is pushing the reaction to the left because we always want to maximize entropy. That's the second law of thermodynamics. And enthalpy is pushing this reaction forward to the products. So that means this reaction is in equilibrium. All right. Then we say, okay, the concentration of products, is that necessarily equal to the concentration of the reactants? This is not true, necessarily. What is true is that if it's in equilibrium, the ratio of concentration of products and reactants is equal, but they're not equal to each other. Concentration of products over the reactants is constant, but it's not true that the concentration of products does not equal the concentration of reactants. That isn't necessarily true. That'd be very unusual. In fact, I could make an argument that it could never be true. And would that hold up to reason? I need to think about that. I think I could make an argument that it is never true. All right. This reaction has reached a state in which no more reactants are being converted to products, and no products are being converted to reactants. That is not what equilibrium means. Dynamic equilibrium is where reactants are always being turned into products, products are always being turned into reactants, because we have these two fundamental forces, pushing in opposite directions. And so at all times, iron and oxygen are being shifted and turned into rust, and some rust molecules, believe it or not, are actually being turned back into iron and oxygen. All right. So this is not true. It's not true that there are no reactants to products or products to reactants, that they're equal in rate, which is what the second one, R, states, that the rate of reactants to products is equal to the rate of products to reactants, and that is true. And the reactants are in a greater state of disorder, so that means entropy, compared to the products. Well, yeah, we said earlier that they have a higher entropy because of these gases. Gases are, we would consider, more disordered, more random in nature. So that is definitely true. So what do I have? A, D, E and F, I, L, N, R, and S are all correct. All right. So let's move on to question 3. All right, so I think we should just be able to go through this one pretty easily here. So side with maximum entropy, so the most random phase. So gas is the most random phase, but this one has 2 gas molecules on the product side, but there's only 1 gas molecule on the reactant side. So we would say this is the most random side. Maximum entropy. Now in the second question, it looks like it's kind of similar. We have these gas phases in all terms. And so then we have to say, well, there are 9 gases on the left, but there's 10 gases on the right. So this looks like there's more gases over here. So we have more species in the most random phase. So this is the products. Okay. Now, here we actually don't need actual phases, pardon me, actual molecules or elements. We could actually do this with general terms. However, it is W and Y actually do correspond, I believe, to specific chemicals, tungsten and yttrium, but I did intend this to be more just general letters. Anyways, whether you treated them as tungsten and yttrium or not, actually we would have had this problem with conservation of mass. Let's move on. Okay, so the question is, okay, we have, what's the most random phase here? Well, it looks like it's gases again. So we have gases here, and we have gases here, but there are two of each. Two gases on each side. Okay, so it looks like those are equally random in terms of gases. There are two of each. So we move to the next random phase, which is our aqueous solution. Aqueous are more random than our liquids, and we have three of these guys. So that makes actually the reactants more random in this case. Okay. And next, we have a question asking, okay, so it's in words. We have a sodium azide pellet in an airbag. I'm going to highlight that. A sodium azide pellet, and when it reacts, it creates solid sodium metal, and it fills the airbag with nitrogen gas. So if I think of a pellet, what do I think in terms of phase? Well, I can think of holding a pellet. That must mean it's solid. So I have sodium azide, that's solid, and it reacts and creates some sodium metal. So it's a solid. Metal is solid, and gas, nitrogen gas, exists in N2s, and it is a, what am I trying to say? It is a diatomic molecule. That's what I was going to go for. All right. Oh, we should probably stop and say, is this balanced? Because that might actually matter. It's not balanced. So I'm just going to go ahead and balance it. I notice I need 3 nitrogens on the left and 2 nitrogens on the right. So I'm going to do a little trick where I swap those values with their coefficients. And that's fine. Now I have 6 nitrogens on the left and 6 nitrogens on the right. But I have 2 sodium, and I only have 1 sodium here, so I need to put a 2 there. All right. Now we're balanced. Anyway, most random maximum entropy. Well, actually, it's the one with the gas. So that's, again, going to be our product. All right, so let's move on. A similar question here. We are asked about minimum enthalpy this time. All right. So we've got this chlorine gas going to aqueous chlorine, and we can tell that we have a negative change in enthalpy. So that means we get a reaction that looks like this, and we lost enthalpy. So that means our reactants, our products, have a minimum enthalpy relative to our reactants. So that's our reactants. Our products here. Minimum enthalpy in this one, well, that actually refers to these terms because you have to add 49.3 kilojoules of extra energy from the system in order for them to have the equal amount of enthalpy to these guys. So when this reacts, it produces and releases energy to the system. So again, this is exothermic, and the products, as a result, have a minimum enthalpy. Quite the opposite here. Our enthalpy of our reactants is quite small, but the enthalpy of our products is quite large. So our minimum enthalpy is here with our reactants. And this shows a increase, positive enthalpy change. We're taking in energy from the system to form these products, and so that vessel will feel cold as a result. All right, and then we got another verbal question. All right, so we've got ammonium nitrate crystals in a cold pack. They dissolve in water. and that makes the pack feel cold. Okay, so it isn't actually very important that we're able to write the reaction. I can write it. It's NH4 NO3 ammonium nitrate, and it dissolves in water. So that's a crystal, so it's a solid, and it's going to dissolve in water, which is a liquid. However, the water is going to be in both sides, so I'm actually going to end up canceling it out. So I end up with some ammonia in an aqueous form and some nitrate in some aqueous form. However, I know that it feels cold. Feeling cold means endothermic, meaning I have to add in energy from the system in order to, I should actually put H, not delta H there. And so I have to add energy, or rather this reaction sucks in energy from the outside. And that's why it feels cold. It's sucking in energy from your fingertips. And so this reaction sucks in energy and is endothermic. And therefore, the minimum enthalpy is in the reactants. Okay, and those are our answers. All right, and then we have a question, moving on to question 5. And this is a 3C thinking question. Okay, so it's going to involve maybe some critical thinking and some analysis and some deeper thought. It's going to require that we, for sure, have all of our basic content and basic knowledge down. It's also going to require that we are sure we know all of our skills that are necessary for this unit. All right, so let's take a look at question 5. So it says we have a reaction. Nitrogen gas reacts with lead to form some lead nitrogen complex. It's kind of weird looking. It's got a subscript 3 and then a subscript 2, which is kind of funny. And it says it doesn't occur. It does not occur. Okay, and the question is it endothermic or exothermic? Is it exothermic or endothermic? Okay. So we're going to have to break this down, I think, and think about it in a few steps. All right. What does it mean if a reaction does not occur? So let's talk about this first. That seems like a pretty key idea. So we know that we have 3 different possibilities, right? We have a reaction could proceed 100%. And if that is true, what can we conclude? If that's true, we know that the products have a minimum enthalpy, and that looks like this, right? So the universe wants to release all stored enthalpy and bonds into the surroundings as much as they can, and so that means this reaction must be exothermic. So a reaction could proceed 100%. It's got to be exothermic, and the products have a maximum entropy. So the maximum entropy means the most randomness. So that's if a reaction proceeds 100%. We know that it would have to be exothermic and that its product would have to be the most random. So alternatively, we could know that a reaction exists in dynamic equilibrium. So if that's true, well, you know what? I'm going to draw some arrows in here to imply that we have a force pushing to the right and another force pushing to the right in this case. All right, I'm going to draw a little dotted line here so I don't get confused there. All right, so if a reaction exists in equilibrium, so that means either the products have a minimum enthalpy and it's exothermic, and the reactants have a maximum entropy. Right? So it's exothermic, but the reactants are the most random. So we have a fundamental force pushing to the right, to the product side, but then we have an equally fundamental force pushing left to the reactant side, and these are in conflict with each other. Or there is another possibility for equilibrium. It could be the opposite. It could be that the reactants have a minimum enthalpy, which means that the reaction is endothermic, and the universe wants to push this reaction to the left. However, there's another fundamental force saying that the products have a maximum entropy, meaning it wants to shift the reaction to the right, and that means that the products are the most random, most disordered. Okay, so those are two different conditions for equilibrium. Either it's exothermic, but the reactants are more random, or it's endothermic, but the products are the most random, most disordered. Okay, well, moving on, we still need to consider what's going to happen if the reaction does not occur. So also possible is the reaction does not occur. And that means both fundamental forces have to be pushing to the reactant side so that this thing doesn't occur. So that means we need some fundamental force, enthalpy force, pushing to the left. So that means that the reactants have a minimum enthalpy. And that means it is endothermic. And our products, pardon me, our reactants have a maximum entropy. So the reactants are the most random. And so both of these guys push this reaction to the left. All right, and that's the case we have now. The reaction doesn't occur. Okay, so in order for that to be true, it must be endothermic, and the reactants have to be most random. Let's just take a look back at the reaction now. All right, where are you, reaction? Okay, so then let's look back here. We have this idea that we have this 3 and 2, and they're a gas, and then we have some lead solid existing, and it forms this guy. So is it true that the reactants are most random? Yeah, it is. The reactants are more random because they have a gas phase. So that means a higher entropy. Okay, and if that's true, that's one fundamental force, the entropy force pushing to the left. That means the enthalpy force has to be pushing to the left, meaning a minimum enthalpy. There's a minimum enthalpy. So for the, I'll write this out as a final statement, for the reactants to have a minimum enthalpy, which is required for a reaction to not proceed. It is endothermic. And that's because if these guys have a minimum enthalpy, then you have to put in energy added to allow the reaction to proceed. Okay, so that's our final answer for question 5. A little bit harder, a little bit more in-depth thinking. Now, you don't have to have necessarily written all this. This is more of an explanation. However, you do have to have understood that if you know that a reaction is exothermic and you can tell which one is more random, you could conclude it doesn't occur. Then if you're told it doesn't occur, you should be able to decide if it's exothermic or endothermic, or which side is more random. And that's something we should be able to determine just by knowing that doesn't occur. In other words, sometimes a 3C problem might involve you taking information and skills you already know how to do in the forward direction, like find the minimum enthalpy and the maximum entropy, and then flip it on its head, flip it backwards. And can you take that idea? If you really understand it, you should be able to apply it in the reverse. All right, let's move on to question 6. Question 6 is another content knowledge question. Just ask, what is Le Chatelier's principle? Le Chatelier's principle is pretty straightforward. I'll write it out here. So not a lot to say here. Le Chatelier's principle is a fundamental force, but it is not a deep force. Le Chatelier's principle states that a system in equilibrium works to minimize changes introduced to the system. Now for full marks, I might indicate what kinds of changes we're talking about here. We're talking about changes in concentration. We're talking about changes in pressure or volume. And we're talking about changes in temperature, not anything else. All right, and that's Le Chatelier's principle. So moving on, we'll go on to question 7. Explain how changing temperature can affect equilibrium concentrations of an exothermic reaction. All right. So I'm just going to get a new piece of paper here. All right, so for question 7, we have a reaction where we know that we have some product in equilibrium with a reactant. That's backwards, isn't it? Some reactant living in concentration with a product, in equilibrium with a product. Pardon me. Okay. And we know that it is an exothermic reaction, meaning going forward is exothermic. Which also means going backwards is endothermic. Okay. So if let's start with an increase in temperature. Oh, also I'm going to say my equilibrium constant, because that's probably going to be important. Oh, no, I'm just talking about equilibrium concentrations, so that's fine. So let's start with an increase in temperature. Increase in temperature will, the reaction want to decrease that temperature. Oh, so I guess the question says explain, so we should probably use some words here. So, but we can also use symbols here. We don't have to write all our words out. So an increase in temperature will cause equilibrium to shift in the endothermic reaction to absorb some of that extra energy. Absorb the extra energy, causing the, it asks us to talk about the effect of the equilibrium concentrations. So we need to talk about how equilibrium concentrations change. So that means as we go in the endothermic direction, there's a decrease in the concentration of our products and an increase in the concentration of our reactants. So similarly, a decrease in temperature will cause equilibrium to shift. So if you decrease temperature, the reaction wants to minimize that by increasing the temperature. So it's going to move in the exothermic direction to release some temperature. The exothermic direction. And that causes an increase in products and a decrease in reactants. Because as we shift to the right, that means more products are made from the reactants. Good. All right, so let's move on. All right, so question 8. I think I'm going to answer that straight on here. Well, maybe I'll just write it. All right. Question 8 says, okay, so we want to explain how the changes that we introduce will affect concentration of water, which is this term, in the following equilibrium. All right, so first is an increase in nitrogen dioxide. So an increase in NO2. How will that change this reaction? So as we increase a product, Le Chatelier's principle wants to minimize that change by shifting equilibrium, taking these products and forming some reactants. So we're going to decrease the amount of each of these so that we can make more of these. So that leads to a decrease in the concentration of H2O. All right. Next, we have an increase in hydrogen peroxide, H2O2. So if we increase H2O2, well, that's going to, Le Chatelier's principle is going to want to decrease that, so it's going to shift it to the right and increase the concentration of both of these guys. So that means we're going to increase the concentration of water. And we're going to increase pressure. And that's going to lead, okay, so in order to answer that, we need to know which side has a higher pressure. So I look, there are 7 gases here, gas species, and there are 2 plus 8, there are 10 gas species over on the right side, so that means this is the higher pressure side. So as you increase pressure, the high pressure side is going to convert to minimize that change and reduce the pressure. So it's going to change into some reactants. As a result, we're going to decrease the amount of water. All right. How about an increase in temperature? Okay, so to answer that, we need to know which is exothermic and which is endothermic in direction. We can see heat is a product, meaning the reaction is exothermic in the forward direction and endothermic in the reverse direction. All right. Now, so if we increase temperature, Le Chatelier's principle is going to want to decrease the temperature and result, minimize that change. So that means we're going to move in the endothermic direction, combining nitrogen dioxide, water, and heat together to make these products, these reactants. But I guess they're products in the reverse direction. All right, so that means an increase in temperature is going to cause a decrease in the amount of water because it's going to be combined with some of these heat molecules extra. And heat molecules, what am I saying? It's going to be combined with some heat energy and some nitrogen dioxide to form products. All right, so that means that we're going to increase the temperature, or that means we're going to decrease the water concentration. Okay. So next, we're going to be looking at a decrease in pressure. All right. So if we decrease the pressure, we have a high pressure side. It's going to want to shift equilibrium to the high pressure side to minimize that change, which means we're going to shift things to the right and take some of these N2H4s and hydrogen peroxides and make them into nitrogen dioxide and H2O. So that's going to cause an increase in water molecules. All right. If we decrease the temperature, then we're going to want to create more temperature to minimize that. We're going to move in the exothermic direction. So a decrease in temperature should lead to an increase in the water. And lastly, we have question G. So a decrease in our N2H4. So if we decrease this amount, equilibrium is going to want to shift so that we can increase that again. So it's going to shift it to the left, making more of the stuff. And it's going to decrease the amount of water as a result. Oops. Okay. All right, so question 9 asks, following equilibria exist in a closed vessel and contains water and gas. Okay, so we can imagine a vessel like a water bottle that has some water in it and some gas in it. Pretty simple stuff here. So, it contains water and gas. Now, there's a bit of a funny thing. I didn't realize this until afterward. Word created a number 10 here. This is not a new question. This is actually part of the original question, question 9. Question 9 by itself doesn't have a question next to it. It's just like, okay, there are some equilibria in a closed vessel, and there's 3 of them. Use these equilibria to explain how a decrease in hydrogen gas, H2, will affect the pH of the solution. All right, so let's just take a look here. If I decrease in my H2 concentration, I don't think I have enough time to finish this question. So I'm going to stop. I'm going to start this video again on the other end. So please go back to Google Classroom if you are finding yourself here on the video, and start the next video down to see the solution to question 9.